Hundreds of millions of years ago, all land on Earth was joined as one, the supercontinent Pangea. It was a world of fire extinction and rebirth, the deadliest chapter in Earth's history. In this video, we'll travel back to that ancient time. If you enjoy it, please like, subscribe, and share, and tell us in the comments would you have survived life on Pangea. Thank you for watching. Now, let's begin. The story of Pangea begins with motion that is almost imperceptible yet unceasing. Beneath the oceans and across ancient continental shelves, the lithosphere shifts and grinds, driven by the slow circulation of heat from Earth's interior. Over millions of years, separate fragments of land, Laurasia in the north and Gondwana in the south, migrate toward one another. These drifting continents close the long-vanished ocean basins that once lay between them, stitching together pieces of crust that had spent eons apart. The process is neither sudden nor smooth. It unfolds through subduction, where dense oceanic plates slide beneath lighter continental ones, and through collisions that thicken crust and lift new mountains skyward. As time moves through the late Carboniferous into the Permian period, these convergences form immense belts of folded rock marking the sutures where smaller landmasses meet. The central core of what will become Pangea lies along a line that stretches from what is now eastern North America through northwestern Africa and into Europe. Here the collision raises a long mountain chain, a precursor to the Appalachians on one side and the Atlas Ranges on the other. Southward, other continental blocks join the growing mass. The collision of what are now South America, Africa, India, Antarctica, and Australia produces another complex seam of uplift and deformation. The supercontinent's growth is not confined to a single event, but an extended series of unions driven by plate movement at rates of only a few centimeters per year. Yet over tens of millions of years, these increments build an entirely new planetary arrangement. By the early Permian, the last stretches of ocean between Gondwana and Laurasia vanish. The closure of the Rake and Paleotethys oceans leaves a single vast landmass that dominates one hemisphere. Around it lies an immense global sea panthalassa, extending almost unbroken around the equator and toward both poles. On the eastern margin of Pangea, a smaller oceanic region remains the Tethys Sea, caught between the converging plates, and destined to evolve into a major marine realm of the Mesozoic world. The union of the continents alters more than geography. It reshapes the face of the planet. The closure of subduction zones reduces volcanic arcs in some regions, while igniting new ones elsewhere. As plates weld together, crustal thickening raises internal basins and mountain uplands that influence air circulation, rainfall, and the distribution of life. The supercontinent's surface, stretching thousands of kilometers from coast to interior, experiences a spectrum of climates that differ sharply between margin and center. Near the coasts, shallow seas and humid air bring periodic rain and temperate conditions. Farther inland, isolation from moisture creates aridity across vast plateaus. These contrasts begin to define the climate character that will later dominate Pangea's history. The land itself bears the marks of unification. Rocks that had once formed in separate depositional environments now share boundaries. Fossil floras that once evolved in isolation appear side by side in the newly connected sedimentary basins. The unification allows species migration on a scale not previously possible. Reptiles, amphibians, and plants expand their ranges across thousands of kilometers of continuous terrain. Yet while ecosystems mingle, the geological record captures the strain of assembly. Folds, faults, and metamorphic zones trace the long lines of impact where continents have collided. Uplifted mountain belts erode, slowly feeding rivers that cross the new continental interior and deposit sediments in broad basins. These sediments later compacted into red beds, will tell future scientists of an arid environment under strong seasonal climates. Pangea's formation also influences the behavior of Earth's deep systems. With a single enormous landmass occupying much of one hemisphere, heat within the mantle redistributes unevenly. Subduction zones once dispersed around the planet now concentrate along fewer continuous margins. The flow of mantle convection adjusts, perhaps slowing in some regions and intensifying in others. These changes in the planet's interior dynamics affect the stability of crustal plates and the location of volcanic provinces. In the long term, they will help determine where stresses accumulate and where eventual rifting will begin. But for now, in the early Permian, the supercontinent stands unified and immense. To visualize the scale of this formation, one might imagine the distance from what will become the northern icebound reaches of Siberia to the southern glacial plains of Antarctica measured not in thousands, but in tens of thousands of kilometers of continuous crust. Deserts, forests, mountain chains, and inland basins all lie within one connected realm. The absence of large intervening seas means that atmospheric patterns extend farther and last longer. Storms born near coastal zones can travel across entire latitudes without obstruction, losing moisture until only dry winds reach the continental interior. The linked land also means that species depending on specific climates may find themselves displaced as conditions shift gradually, from humid to dry, from temperate to extreme. The connection between climate and life, between tectonics and biology, becomes more direct and more global than ever before. The evidence for this assembly remains visible in the rock record scattered across modern continents. Similar fossils, identical mineral compositions, and aligned mountain ranges on opposite sides of the Atlantic and Indian Oceans all point to the once-joined configuration. Magnetic minerals preserved in ancient lava flows reveal consistent orientations that, when reconstructed, trace the slow drift of the continents into their Permian alignment. Radiometric dating confirms the timing of collisions and the sequence of sutures. Taken together, these clues reconstruct an image of a world dominated by unity rather than separation. By the close of the early Permian Earth's surface enters a rare interval of stability at the larger scale. The supercontinent has gathered almost all major continental crust into one continuous expanse. The remaining oceanic crust, vast and deep, covers most of the globe but carries little of the shallow marine diversity that earlier eras supported. The balance between land and sea, critical to climate regulation, is now heavily tilted toward land dominance. This will have profound effects on atmospheric circulation, rainfall patterns, and global temperature gradients. Yet at this stage, the world still holds equilibrium. The new arrangement brings neither catastrophe nor abrupt upheaval, only gradual change accumulating through time. Pangea stands as both culmination and prelude, the product of long tectonic convergence, and the stage for transformations that will follow. As erosion subsidence and continental motion continue without pause, the newly unified land begins to develop its distinctive patterns of desert and forest, of mountain and plain. The forces that brought it together will, in ages still distant, begin to pull it apart again. But for now, in the quiet span of early Permian time, the planet rests under a single horizon of rock and sky. With the continents fused into one immense body, the Earth of the early Permian settles into a new geometry unlike any before. On maps reconstructed from magnetic and sedimentary evidence, nearly all dry land lies gathered as a massive oval, stretching from the northern high latitudes deep into the southern hemisphere. This landmass, known as Pangea, occupies roughly 1/3 of the planet's surface, while the remaining expanse is an ocean without rival. The global sea surrounding the supercontinent Panthalassa encircles Pangea from every side, vast and continuous, a single marine realm, spanning more than half the circumference of the world. Its surface currents sweep unbroken for tens of thousands of kilometers, tracing slow gyres around the equator and sinking into abyssal depths where circulation weakens. The configuration of one land and one sea profoundly alters the planet's climate tides and life. The vastness of Pangea shapes the behavior of air and water together. Heat absorbed at the equator flows outward toward the poles, while cold, deep currents return toward tropical regions. In this simple but enormous oceanic system, variations of temperature and salinity determine how water moves between surface and depth. Because most coastlines now belong to one perimeter, the connection between atmosphere and ocean strengthens. The winds that blow across Pangea can gather moisture for thousands of kilometers before striking the continental margins of Pangea, releasing sudden torrents that feed the growing monsoonal systems along its edges. The interior, distant from any sea, lies under the opposite extreme where rain rarely penetrates, and surface waters evaporate under dry air. The union of land also changes how sunlight and heat are distributed. Continents absorb and release warmth differently than water. With so much land concentrated in one mass, seasonal contrasts intensify. In the long summers of the southern regions, air heats rapidly and rises in great convection, cells drawing moisture-laden winds from the sea toward the coasts. In winter, the same vast interior cools more quickly than the surrounding ocean, reversing circulation and sending cold, dry air seaward. This exchange becomes the pulse of the planet's new climate rhythm, a pattern of planetary monsoons extending across hemispheres. Pangea itself is not uniform. Beneath its broad surface lie trenches, ridges, and volcanic arcs, formed by subduction zones that encircle the supercontinent's margins. These active boundaries generate island chains and deep basins, where new crust forms and old crust descends into the mantle. Far from land, in the central ocean, sediments accumulate slowly fine clays, volcanic ash, and the shells of microorganisms settling over eons. These deposits will later record the chemistry of ancient waters, preserving evidence of oxygen levels and carbon balance that change with time. Around the continental edges, the sea remains shallower and more dynamic. Here, reefs, lagoons, and deltas form in repeating patterns, building strata rich with fossils that mark transitions in marine life. At the global scale, the balance between continents and oceans exerts powerful influence on atmospheric gases. When the continents join, weathering of rock increases along new mountain chains, drawing carbon dioxide from the air through chemical reactions with silicate minerals. Over geological time, this gradual drawdown of carbon dioxide can cool the planet, affecting both climate and sea level. The resulting cooling may encourage glaciation in polar regions while promoting dryness at the equator. Yet feedbacks in the system are complex. As continental interiors grow arid, less weathering occurs there, limiting further cooling. The climate of the Permian world thus stabilizes within narrow but extreme bounds, alternating between hot and cold, wet and dry, with strong contrast between regions but relative balance over the long term. The arrangement of a single global ocean also influences the chemistry of the deep sea. Circulation between surface and abyss becomes sluggish, because only a few narrow gateways exist where dense water can sink. This restricted flow allows oxygen to decline in deep layers over time, creating broad zones of low oxygen known as anoxia. These zones expand and contract with climate shift, shaping where marine organisms can survive. In later ages, as volcanic gases alter atmospheric composition, these low-oxygen regions will become critical to the chain of events leading to mass extinction. But in the early Permian they remain stable features of a world adjusting to its new form. Across Pangea's perimeter, geological activity continues. Subduction zones consume older oceanic crust, volcanic arcs rise, and earthquakes trace the dynamic seams of the planet's single vast tectonic circuit. The interior, in contrast, remains geologically quiet. Cratons, ancient stable portions of the continental crust, form the heart of the supercontinent, their roots descending deep into the mantle. Around them stretch basins filled with red sandstones and evaporates, the products of continental deserts and drying lakes. These sediments, rich in iron oxides, give the rock record of this era its distinct colour, a reflection of oxidizing conditions under a dry atmosphere. The effect of this configuration on life is far-reaching. On land, the continuity of terrain allows species to disperse widely, blurring the regional distinctions that once existed among separate continents. Yet the aridity of the interior limits diversity. Vegetation clusters along river valleys and coastal plains where water persists. Forests of conifers and seed ferns dominate the moist margins, while in the vast dry basins only hardy plants adapted to drought survive. In the oceans, the opposite trend unfolds. Shallow marine habitats flourish along the long continuous continental shelves of Pangea. Here reefs of sponges and corals, shoals of brachiopods, ammonoids and early bony fishes thrive in clear warm waters. These marginal seas, though narrow in width, extend for tens of thousands of kilometers, forming ribbons of high biological productivity around the supercontinent's edge. Panthalassa's immensity also stabilizes global sea level. With so little continental breakup, the volume of ocean basins changes slowly. Tides generated by the gravitational pull of the moon and sun sweep around the world in immense waves, rising and falling across the broad coasts of Pangea with predictable rhythm. These cycles influence sedimentation patterns, building rhythmic layers of sand and mud that geologists will later read like pages of a vast continuous diary of time. From space, if such a perspective had been possible, the planet at this stage would appear strikingly simple. A single continuous continent tinted in bands of brown and red stretches across one hemisphere. Surrounding it, a seamless blue ocean reflects sunlight over the other. Cloud systems swirl around the margins where warm, moist air from Panthalassa meets the rising heat of the land. Over the interior, skies are often clear and dust carried by winds marks the boundaries of growing deserts. The contrast between oceanic uniformity and continental complexity defines the physical world of the Permian. Beneath the stillness of its surface, however, the Earth remains restless. Convection continues deep within currents of molten rock, circulating below the rigid plates. The same forces that once drove the continents together are not extinguished. They merely shift direction. For the moment, the supercontinent endures as a stable entity, but strains accumulate invisibly in its crust. These tensions, balanced for now, will one day reopen the seams of union. The world stands at equilibrium, one land, one sea, one climate system spanning the globe, poised between the long calm of assembly and the upheavals that lie ahead. Within the borders of Pangea lies an expanse so great that it defines the environmental character of an age. From the margins where waves from Panthalassa break against rocky shores, the land stretches inward for thousands of kilometers before meeting another coast. The continental interior, distant from moisture-bearing winds, becomes a realm of extremes, arid plains, salt flats, and seasonal rivers that rise and vanish with the rhythm of fleeting storms. Across this interior, temperatures swing from searing heat in the long summer to biting cold in the short winter. The ground bakes beneath a high sun, forming thick crusts of evaporated minerals. dust lifts easily, carried by turbulent winds across open plateaus. In these deserts, vegetation is sparse, limited to low shrubs and hardy seed ferns that can endure drought. Yet the barrenness is not absolute. Along faulted basins and ancient river valleys, occasional water gathers in shallow lakes. Here life clings to persistence, forming oases of green where amphibians, small reptiles and early therapsids, the ancestors of mammals, find sustenance. These isolated refuges break the monotony of the supercontinent's interior, forming scattered pockets of productivity amid a vast dry land. The geometry of Pangea dictates these contrasts. A continent of such size hinders the inward flow of humid air from the ocean. When winds from Panthalassa reach the interior, most of their moisture has already fallen as rain along the coastal margins. Only dry, heated air continues onward, descending and intensifying the aridity. This circulation forms a system of high-pressure zones that suppress cloud formation over much of the land. Evidence for this pattern survives in the rock record red beds of oxidized sandstones and conglomerates spread widely across what are now North America, Europe and Asia recording deposition under well-oxygenated terrestrial conditions. These rocks preserve the fingerprints of ephemeral streams and wind-blown dunes, silent witnesses to the great deserts that once stretched across the heart of Pangea. Along the coast the story changes. Marginal seas, broad, shallow bodies of water, lying between the continental shelf and the open ocean, form narrow ribbons of humidity around the supercontinent's edge. These seas moderate the local climate, providing moisture that sustains forests and fertile floodplains. In the equatorial zones, monsoonal winds bring seasonal rains that feed dense vegetation. Swamps and coal-forming wetlands thrive especially in regions that correspond to modern-day China and parts of Eastern Europe. Here, thick accumulations of plant matter under humid conditions create the organic, rich layers that will later transform into coal seams. This contrast between arid interior and lush margin marks one of Pangea's defining features, a single landmass hosting both extreme deserts and verdant coastal belts. In the high latitudes, cold conditions prevail. Near the poles, long winters and low sun angles produce cool climates that encourage coniferous forests and tundra vegetation. The combination of broad latitudinal range and continental scale ensures that nearly every terrestrial environment of the time finds place upon this single continent. Yet the continuity of terrain allows for wide dispersal of species. Fossil evidence of identical plant genera found across distant parts of the world today, such as Glossopteris in the south and Chordates in the north, shows that these once flourished across contiguous regions of Gondwana and Laurasia. The absence of oceanic barriers promotes exchange between biotas that had once evolved separately, uniting ecosystems, just as tectonics united land. Sediment carried from the interior toward the coasts shapes the geography of the marginal seas. Rivers born in mountain belts erode vast quantities of material, depositing it into deltas and shallow basins. In these regions, the interaction of fresh and marine waters produces layers of alternating sand, silt and limestone. As tides rise and fall along the edges of Panthalassa and the smaller Tethys sea currents, stir nutrients that feed extensive marine ecosystems. Coral-like organisms and sponges build reefs while mollusks and early crustaceans occupy the muddy flats. The sedimentary record captures the rhythm of these coastal environments, their alternating wet and dry seasons, and the steady accumulation of organic matter that supports complex food webs. The contrast between interior and margin also shapes atmospheric chemistry. Dust from arid zones becomes an important carrier of minerals lifted by wind and transported across the continent. When storms reach the coast, Rain washes this dust into rivers and seas, supplying nutrients such as iron and phosphorus that stimulate marine productivity. The linkage between desert and ocean thus operates as a subtle but global exchange of materials. Over long intervals, it influences carbon cycling by regulating how much organic carbon is buried in sediments versus returned to the atmosphere. Beneath the surface, tectonic stability continues to define the continental core. With few active boundaries within the interior, crustal deformation is minimal. The absence of significant volcanic activity reduces atmospheric aerosols, allowing clearer skies and strong solar heating. However, along the periphery, subduction zones remain active. Volcanic arcs form belts of uplifted terrain where new land emerges from the sea. These volcanic margins create natural laboratories of ecological renewal with fresh soils and shifting coastlines. They also act as conduits for gases exchanged between Earth's interior and atmosphere processes that, though balanced now, will one day tilt toward imbalance. Pangea's sheer scale also affects the movement of water across its surface. Rainfall that falls along the coast must travel enormous distances to reach interior basins. Rivers lengthen, accordingly, carving wide valleys and carrying sediments through varied climatic zones. Floodplains develop immense braided systems where channels migrate and overlap, leaving intricate patterns preserved in stone. When rainfall weakens, these rivers retreat, leaving behind dunes and Playa Lake's flat depressions that fill temporarily during storms and then dry to form salt-encrusted plains. Such cyclical environments reflect the fluctuating balance between precipitation and evaporation that defines continental climates. Despite the harshness of its heartland, the interior of Pangea is not lifeless. Fossils reveal traces of reptilian footprints pressed into ancient mud trackways, of animals moving between seasonal pools and burrows that sheltered creatures from heat. These glimpses suggest that life adapted not by abundance but by resilience. In the shade of sparse vegetation, and in the shelter of eroded rock, small communities persisted through the long cycles of drought and rain. Their endurance forms part of the continuum connecting this dry era with the more temperate worlds that will follow. The meeting place between the arid interior and the wetter margin becomes a critical ecological boundary. Here, climatic gradients sharpen, driving evolutionary innovation. Plants develop deeper roots and more efficient water storage, while animals adapt to migration between habitats. Over millions of years, these transitions shape the diversity that will later recolonize the Earth after catastrophe. As the Permian period advances, the features of the supercontinent grow more pronounced. Deserts expand, mountain belts erode, and marginal seas deposit thick successions of limestone and shale. Each process records the balance between land and sea dryness, and moisture stability and motion. The Earth of this time appears static when viewed from the scale of human thought, yet within its quiet cycles lie the forces that will soon change the course of life itself. The interior vastness of Pangea endures as both monument and warning, a world unified yet divided by its own immensity, holding within it the beginnings of the planet's greatest transformation. Above the unified landmass of Pangea, the atmosphere adjusts to a pattern both immense and unstable. With continents joined from pole to pole and oceans pushed outward into a single encircling basin, the flow of air evolves into broad planetary-scale cells of motion. Heat from the sun, strongest along the equator, rises and drifts toward the poles, driving continuous circulation that touches every region of the supercontinent. The presence of such an enormous land surface alters this balance in ways unseen in earlier ages. Land absorbs sunlight more quickly than water, and releases it faster when the night comes. This difference produces violent contrasts between day and night, between coastal moisture and interior dryness. Winds strengthen as air masses shift to equalize temperature across thousands of kilometers. In summer, heated air expands above the continental interior, drawing moisture-laden winds from Panthalassa. When these winds reach the coast, they rise cool and release rain in sudden deluges. This marks the height of a continent-scale monsoon system that extends from one hemisphere into the other. For months, torrential rains wash over river plains and deltas, feeding vegetation and filling inland lakes. But the reach of this moisture is limited. By the time these air masses cross mountain ranges and reach the central deserts, their water has already fallen. The rains cease, the air warms again, and dust replaces cloud in the empty sky. When winter comes, the direction of movement reverses. The supercontinent cools faster than the surrounding ocean, creating a dome of high pressure over the land. Cold, dry air flows outward toward the sea, suppressing clouds and lowering temperatures across the interior. Frost settles even in low latitudes, while coastal margins experience cold winds that chill the shallow seas. These alternating patterns of wet and dry, hot and cold define Pangea's climate. The annual cycle is extreme, magnified by the vast distance between the center of the landmass and the moderating influence of the ocean. In the geological record, this alternation leaves rhythmic patterns, bands of clay and silt deposited by seasonal floods, evaporate layers formed during dry intervals, and cross-bedded sands shaped by alternating wind regimes. Each layer marks the steady breathing of the planet's atmosphere over the supercontinent. The circulation above Pangea extends beyond simple alternation. Because the continent stretches from near pole to pole, global wind belts that once curved freely across oceans now encounter land for thousands of kilometers. At the equator, rising warm air forms a permanent belt of convection, while to the north and south, subtropical high-pressure zones bring persistent dryness. These belts migrate with the seasons, carrying the boundary between desert and savanna northward and southward each year. The highlands that cross Pangea influence these flows further. The mountain chains left by continental collisions act as barriers, redirecting winds and creating rain shadows. On the windward slopes, precipitation feeds streams and forests. On the leeward sides, aridity deepens. This pattern, seen today in fossilized dune fields and ancient soil horizons, reveals how topography governed local climates within the broader global scheme. In the polar regions of Pangea, long winters and limited sunlight generate cold air masses that drift equatorward. Where these meet warmer air from the tropic storm systems form their intensity fueled by the steep thermal gradient across latitudes. Yet because most of the northern and southern extremes lie on land, these storms behave differently than modern oceanic cyclones. They lose moisture quickly, their clouds thin, and instead of long-lived hurricanes, the planet experiences shorter, drier tempests that move dust rather than rain. The upper atmosphere, too, reflects this arrangement. With fewer large seas to supply evaporative moisture, the overall humidity of the planet declines. Skies remain clear for much of the year, and incoming solar radiation reaches the surface with minimal scattering. The result is a climate of extremes alternating between scorching days and frigid nights, between short seasons of rain and long intervals of dryness. Despite this harshness, the atmospheric system is stable in its pattern. The high-altitude winds, known as jet streams in modern terms, trace wide circuits between the hemispheres, following temperature gradients across the supercontinent. These steady flows distribute dust seeds and volcanic aerosols around the globe, linking distant regions through air alone. Over the course of the Permian, these connections help synchronize climate changes across the planet. A cooling event recorded in one basin appears almost simultaneously in others, reflecting the speed with which air now circulates over a connected world. Oxygen and carbon dioxide levels in the air also shift with time. During the early Permian, atmospheric oxygen remains relatively high, supporting large animal life and widespread wildfires. Charcoal fragments in sedimentary rocks testify to the frequent burning of dry vegetation fires sustained by oxygen-rich air and seasonal winds. As the climate warms and aridity expands, these fires become more common, reshaping ecosystems and releasing carbon back into the atmosphere. Over time, volcanic outgassing, chemical weathering, and biological processes together regulate these gases, maintaining a dynamic equilibrium. Yet even small fluctuations can alter global temperature, influencing the strength of monsoons and the extent of deserts. Dust carried by the wind becomes a key component of this system. The fine particles lifted from the interior deserts form vast plumes that drift thousands of kilometers before settling. They fertilize marginal seas with minerals and trace elements stimulating plankton growth. At the same time, these airborne minerals reflect sunlight back into space, subtly cooling the surface. The climate of Pangea thus becomes a self-regulating network of feedbacks between land, air, and ocean, balanced but delicate. The planet's energy budget, how much sunlight it absorbs versus how much it reflects, depends increasingly on the composition of its atmosphere and the color of its continents. During the height of summer, the sky over Pangea's interior glows pale and clear. Winds move in slow, shimmering waves carrying heat outward. Dust devils spiral across the plains, rising high enough to merge with the haze of the upper air. At sunset, temperature drops rapidly and heat radiates back into space. Frost sometimes forms by dawn, even after days of intense heat. Along the coastal margins, in contrast, humid air condenses into clouds that drape the forests and deltas. Lightning flashes through monsoon storms, and torrential rain erodes the mountains, sending torrents of sediment toward the sea. These alternating moods of the atmosphere, serenity, violence, stillness, are the daily rhythm of a planet whose scale magnifies every process. The long-term effect of this atmospheric arrangement is the establishment of global wind patterns that persist for tens of millions of years. The fossilized orientation of dunes, the direction of cross-bedding in sandstones, and the chemical signatures of ancient soils all confirm the dominance of strong, consistent airflows. In this sense, Pangea becomes a climate engine whose stability allows predictable weather, yet whose extremes push ecosystems to their limits. It is an environment governed not by chaos, but by immense regularity, where the pulse of the seasons is written in stone. Above this world, the air carries dust, moisture, and gases in endless circuits, binding the planet into one continuous atmospheric whole, a supercontinent beneath and a super sky above. Encircling the supercontinent, the waters of Panthalassa form the greatest ocean the planet has ever known. Its vastness shapes every aspect of the Earth's surface environment. Spanning from pole to pole, it connects all marine regions into a single continuous system. Yet within this apparent uniformity lie immense differences of depth, temperature, and chemistry. Near the equator, warm currents drift westward under steady winds, accumulating heat in wide gyres that move slowly across the open sea. In the high latitudes, colder waters descend, driving sluggish, overturning that transports oxygen and nutrients to the deep. The interaction of these zones creates a global oceanic circulation of extraordinary scale, though one limited by the geometry of Pangea. With only a few narrow pathways between surface and depth, the exchange of water masses becomes inefficient, and regions of the deep ocean gradually lose oxygen. In the geological record, black shales rich in organic matter testify to these oxygen-poor basins. that first begin to appear in the Permian. Around the margins of Pangea, where continental shelves meet the open ocean, the pattern of circulation is more dynamic. Here, tides and monsoon-driven currents mix warm saline surface waters with cooler inflows from the abyss. Seasonal upwelling along certain coasts brings nutrients from the deep to the light-filled shallows, sustaining dense populations of plankton. These blooms feed trilobites in their final days, ammonoids, brachiopods, and the ancestors of modern fish. Coral-like organisms and sponges form reef structures in the clearer equatorial seas, building mounds of calcium carbonate that rise toward the sunlight. Between the reefs, broad lagoons support mollusks and crustaceans, while beneath them, worms and burrowing creatures turn the sediment maintaining oxygen flow within the seabed. The water here is calm and fertile, a contrast to the emptier expanses of the deep Panthalassan interior. The smaller Tethys Sea, positioned along the eastern edge of Pangea, plays a different role. Sheltered between converging continental margins, it becomes a cradle for marine diversity. Its geography allows for shallow connections between equatorial regions and subtropical latitudes, creating gradients of temperature and salinity that foster evolutionary variety. Over millions of years, these warm, semi-enclosed waters will host the early ancestors of many Mesozoic marine forms, from ammonites to marine reptiles. In the Permian world, it stands as one of the most vital marine provinces, its coral and algal reefs rivaling those of Panthalassa's western shelves. The chemistry of these oceans reflects the balance between volcanic outgassing, weathering of continental rocks, and biological productivity. Carbon dioxide dissolves from the atmosphere into seawater, forming carbonic acid that reacts with calcium and magnesium ions to create carbonate minerals. This process helps regulate planetary temperature by storing carbon within marine sediments. However, the stability of this system depends on circulation. When deep waters stagnate and oxygen levels drop, the decomposition of organic matter slows and carbon accumulates in dissolved form, ready to be released again if conditions change. Such feedbacks make the ocean both a buffer and a potential source of atmospheric shifts. During the late Permian, subtle changes in temperature or salinity could tilt this balance, altering the global climate with consequences that would ripple through ecosystems. Ocean life in this era still carries echoes of the earlier Paleozoic world. Brachiopods cover the seafloor like living carpets, their shells opening and closing in rhythmic unison. Crinoids. The feathered relatives of sea stars anchor themselves to limestone reefs, filtering plankton from the passing currents. Sharks and primitive bony fishes patrol the deeper channels, while nautiloid and ammonoid cephalopods drift through open water, their coiled shells regulating buoyancy as they hunt. The diversity of marine forms reflects a stable and interconnected system, one that has recovered from earlier crises and seems for the moment balanced. Yet the sedimentary layers laid down in these seas record more than abundance. Shifts in isotopic composition show gradual changes in ocean temperature and chemistry, silent indicators of stresses building within the global environment. The physical energy of Panthalassa is immense but predictable. Tidal waves travel unimpeded around the world, their amplitude reduced by the sheer scale of the basin. Storms form mostly along the equatorial belt, where warm water and strong evaporation feed vast cloud systems. Cyclones follow the same tracks year after year, bringing seasonal disturbance to the coastal margins. Lightning illuminates the surface, striking waves that tower over shallow reefs. Rain from these tempests returns nutrients to the sea, while runoff from the continents delivers sediments that cloud the nearshore waters. Each monsoon cycle reshapes the continental shelves, eroding some regions and building new deltas elsewhere. These repetitive patterns define the Permian marine landscape as much as tectonic forces do. The interplay between land and sea becomes especially visible along the continental margins of what will one day be western North America and northern China. There, the meeting of oceanic and continental plates generates deep subduction trenches. Water carried down with the sinking crust triggers volcanic activity on the overriding plate, producing island arcs and mountain chains. Hydrothermal vents at these margins release hot mineral-rich fluids that sustain ecosystems independent of sunlight. Bacteria thrive around the vents, feeding entire communities of tube worms and crustaceans. Although isolated in the darkness, these oases mirror the balance of chemical energy that underlies life across the oceans. In the open sea, far from any coast, currents move slowly beneath a sun that rises and sets over water for endless horizons. Floating organisms, some microscopic and others the size of small fish, drift where light penetrates the surface. Their collective activity drives much of the planet's oxygen production and carbon cycling. At night, bioluminescent plankton glimmer faintly, marking the gentle movement of waves. Beneath them, deeper layers remain calm, stratified by temperature and salinity into distinct zones that rarely mix. It is in these quiet depths that the first signs of change begin to appear. Reduced oxygen-altered chemistry, a subtle decline in biodiversity. Though still far from crisis, the ocean system shows hints of approaching imbalance. The sea level during this period remains relatively stable, regulated by the slow creation and destruction of oceanic crust. Yet even small fluctuations affect the distribution of marine habitats. When sea level falls, reefs are exposed and die, leaving barren limestone flats. When it rises, new environments form and life quickly recolonizes them. This dynamic shoreline, moving over hundreds of thousands of years, contributes to the complex layering of sedimentary rocks that now serve as the geologic memory of Panthalassa's rhythm. From a planetary perspective, the waters around Pangea act as both mirror and moderator of the supercontinent's climate. They absorb heat during the warm seasons, release it during the cold, and carry moisture that fuels monsoons. They buffer the composition of the atmosphere by exchanging carbon and oxygen with the biosphere. Yet this balance, sustained for millions of years, depends on continued circulation between surface and depth. As tectonic rearrangements and volcanic activity later interfere with this flow, the equilibrium will falter. But for the moment, in the calm center of Permian time, the world's oceans are whole. They spread unbroken and immense, their tides linked to a single land, and a single sky recording in silence the slow approach of change. The climate of Pangea in the later Permian is an exercise in contrasts. With a single landmass spanning nearly an entire hemisphere, differences between the interior and the coasts reach their greatest expression. The supercontinent's geometry amplifies every element of weather: the heat of its summers, the cold of its winters, the violence of its storms, and the persistence of its droughts. From pole to pole, air circulates along vast predictable paths carrying moisture only so far before releasing it and leaving the inland reaches parched. Across what is now Central Asia, North America, and Northern Africa, broad belts of desert extend for thousands of kilometers, their dunes forming rippling seas of red sand under an unbroken sky. The dryness is intense, not simply because of distance from the ocean, but because of the physics of air and stone. Sunlight absorbed by the dark surface radiates back into the atmosphere, creating layers of hot, stable air that block cloud formation. Daytime temperatures rise high, while at night, with no moisture to trap heat, the ground cools rapidly, freezing the shallow depressions where ephemeral lakes form after rare rains. the pattern of monsoons around the coast continues to dominate the margins. In the low latitudes, seasonal winds from Panthalassa bring torrents of rain to the eastern edges of the continent. Forests of conifers and seed ferns flourish there, and great rivers spread sediment across wide floodplains. Yet even these regions oscillate between abundance and scarcity, for when the winds reverse, in winter the rain ceases and the soil hardens. The annual rhythm of wet and dry seasons creates layered deposits of mudstone, siltstone, and evaporite, each marking the alternation of flood and drought. These sediments, rich in iron oxide, preserve a record of an atmosphere that is oxygen-rich, but steadily changing in composition, as vegetation, weathering, and volcanism trade gases between earth and air. At higher latitudes, the story is different. Near the poles, long winters and low sun angles keep temperatures low. Glacial remnants persist in the far southern regions of Gondwana, where ice sheets occasionally advance over rocky plateaus. Seasonal meltwaters carve channels and deposit gravels, recording the continued but waning influence of an ice age that began millions of years earlier. Between the polar cold and equatorial heat stretches a transitional belt of temperate climate, where deciduous plants and conifers coexist. These middle zones experience pronounced seasonality, their growing cycles governed by extremes of light and darkness, rather than rainfall alone. The composition of the atmosphere during this time amplifies these climatic zones. Oxygen levels, though still higher than today, begin a slow decline, while carbon dioxide concentrations rise slightly, as volcanic activity releases gases from Earth's interior. The balance between these gases determines how much heat the planet retains. As carbon dioxide increases, global temperature rises a few degrees, but the presence of the immense landmass prevents even distribution. Oceans, which would normally carry heat from the tropics to the poles, are confined to the planet's opposite hemisphere, leaving continental interiors without moderating influence. The result is a patchwork of microclimates layered across a world unified in geography but fragmented in experience. Evidence of these conditions lies in the rocks themselves. Evaporites, salts left behind by the drying of inland seas, accumulate in thick beds across regions corresponding to modern Europe, North America and the Middle East. Gypsum halite and anhydrite form under intense evaporation, signalling that vast shallow basins repeatedly filled and emptied. Cross-bedded sandstones preserved in sweeping arcs record the action of constant wind over open ground. These desert formations stretch across entire continents, their orientations consistent with prevailing trade winds inferred from modern physics. In other areas, coal-bearing strata mark pockets of persistent humidity near the coasts, evidence of strong climatic zoning within a single planetary surface. Lightning storms frequent in the monsoon belts ignite wildfires that spread rapidly through the dry forests at the edge of deserts. Charcoal fragments trapped in sediments confirm that fire is a regular feature of the Permian landscape. These blazes release carbon dioxide and create open ground for new growth, establishing a cycle of destruction and renewal that shapes the vegetation cover. The combination of abundant oxygen and widespread dryness makes such fires more intense than those in later ages. From space, had it been visible, the planet would have shown streaks of smoke curling over vast regions, their plumes drifting across continents under the high winds of seasonal exchange. The variability of climate also influences ocean behavior. Extended dry periods increase the delivery of mineral dust into the seas, enriching surface waters and stimulating bursts of biological productivity. When these blooms collapse, organic matter sinks and decays, consuming oxygen in the lower layers of the ocean. Over millions of years, this gradual process leads to expanding anoxic zones in the deep Panthalassan basin. Although not yet catastrophic, these conditions hint at a fragile equilibrium between land atmosphere and sea, an equilibrium that will later be broken. On land, the adaptations of plants and animals mirror the rhythm of climate. Seed ferns and early conifers evolve traits to resist water loss, such as thick cuticles and needle-like leaves. Reptiles develop more efficient respiratory systems and eggs that can survive dry conditions, allowing them to colonize environments once limited to amphibians. The growth rings in fossilized wood show alternating periods of rapid and slow development, revealing that even the trees of this era record the pulse of the monsoon. In the arid belts, only scattered oases support life, but along rivers and seasonal lakes, entire ecosystems flourish for part of each year before retreating under the returning sun. Across the supercontinent, winds sculpt the landscape continuously. Dust settles in layers that harden into loess deposits, marking repeated cycles of erosion and transport. In some regions, dunes reach heights of hundreds of meters, their slip faces frozen in time as ancient cross strata. The interplay between wind and rock defines the visual character of Pangea's heartlands, a continent of ochre tones and shifting horizons. Far to the north and south, glaciers and permafrost remain as vestiges of cooler climates, providing sharp contrast to the equatorial deserts. The coexistence of frost and drought on a single landmass demonstrates the range of conditions the supercontinent sustains simultaneously. Despite its severity, this climate fosters stability. The extremes follow predictable patterns and ecosystems adapt in place. Over millions of years, the atmospheric composition, ocean chemistry, and solar input remain in rough equilibrium. The world of the late Permian, though harsh, is steady, a balance that masks its underlying fragility. Deep within the earth, magma accumulates in vast chambers beneath what is now Siberia, preparing a transformation that will soon disrupt the atmosphere and oceans alike. For now, the surface shows no sign of what lies beneath. Deserts expand and contract with the seasons. Forests shed their leaves and regrow, rivers carve through red stone, and the winds continue their endless circuits over one land and one sea. The climate system of Pangea stands as a monument to the power of geometry and the persistence of motion, a planetary balance stretched across the edge of change. Across the vast surfaces of Pangea, life persists in patterns shaped by geography and climate. The supercontinent's unity allows species to move freely from one end of the world to the other, yet its extremes of temperature and moisture limit where most can survive. On the coastal plains and humid margins, forests of conifers, cycads, and towering seed ferns form dense canopies, their roots binding floodplain soils, and their fallen trunks accumulating in thick beds of peat. These forests are home to amphibians, reptiles, and early synapsids, creatures that blend reptilian bodies with mammalian features, dominant both as predators and herbivores. Further inland, where rainfall grows scarce, vegetation thins into hardy shrubs and spore-bearing plants adapted to drought. Here the landscape is open, the horizon broken by dunes, and the occasional river lined with dark green trees. In these dry basins, the air shimmers with heat, and the animals that live there move slowly, conserving water and sheltering in burrows during the day. The unity of the land encourages migration. Fossils of similar plant species are found across regions that now lie thousands of kilometers apart, evidence that the continuous terrain allowed wide dispersal. Glossopteris, a fern-like tree, grows across the southern portion of Pangea, from what is now South America to Antarctica and India, its leaves adapted to cooler climates, but still dependent on seasonal moisture. In the north, Vast forests of conifers and seed ferns dominate the temperate zones, their needles and leaves forming a dense litter that feeds decomposers in the soil. The spread of these plants alters atmospheric chemistry by absorbing carbon dioxide and releasing oxygen, a slow exchange that influences global temperature and the frequency of wildfires. Beneath their branches, synapsids such as Dimetrodon and Edaphosaurus thrive. They are not reptiles in the modern sense, but part of a lineage that will one day give rise to mammals. Their sprawling limbs carry them through river valleys and floodplains, their sails, extensions of vertebral spines, perhaps aiding in thermoregulation under the changing sun. The variety of terrestrial life during this era reflects both adaptation and opportunity. The unification of continents eliminates geographic isolation, allowing dominant groups to spread widely. Amphibians continue to depend on water and inhabit the low-lying swamps while reptiles and synapsids expand into drier zones. Herbivores graze on low vegetation, and carnivores follow in turn, creating balanced ecosystems that stretch across entire regions. Insects already diverse pollinate plants and act as decomposers, breaking down organic matter into the nutrient cycles that sustain these vast ecosystems. The soils of the time are rich in iron and mineral salts coloured by the oxidation that accompanies life in an oxygen-rich atmosphere. Along the coastal zones, different communities emerge. Where the monsoon rains feed deltas and estuaries, vegetation forms thick belts of wetland flora. Here amphibians grow large, some reaching lengths of several meters, their broad heads and flat bodies suited to both land and water. Crocodile-like predators lurk in shallow pools, waiting for fish or small terrestrial animals to approach. The interplay between land and water creates a dynamic environment in which each flood and drought reshapes the ecosystem. These lowlands, fed by sediment from distant mountains, form the coal beds that record the humid intervals of Pangea's climate. As one moves inland, the biological richness fades, replaced by species adapted to scarcity. Reptiles develop thicker scales to reduce water loss, and their eggs enclosed in protective shells free them from dependence on aquatic habitats. Early therapsids with more advanced lungs and metabolic control roam widely over arid plains. Their skeletons show evidence of upright posture, a step toward the efficient locomotion that will later characterize mammals. These animals dominate the food chains of the late Permian, their diversity unmatched by any previous vertebrate group. The most successful species combine resilience with adaptability, able to tolerate fluctuations of temperature and limited food supply. In the far southern regions of Gondwana, where cool conditions persist, other forms of life find refuge. Thick forests of Glossopteris and Gangamopteris cover the floodplains, shedding leaves each winter as light fades. Here, primitive amphibians and early reptiles coexist with giant insects that thrive in oxygen-rich air. Seasonal ice and thaw produce braided rivers, their sediments preserving impressions of leaves and tracks. This high-latitude environment, though cold, remains stable compared to the volatile climates of the equator. Its ecosystems endure almost unchanged for millions of years. The unbroken expanse of Pangea also allows the spread of diseases and parasites, linking ecosystems in a new way. The same continuity that permits migration also connects vulnerabilities. Local disturbances can ripple across regions as species move freely, yet such challenges also accelerate evolution. The absence of barriers fosters competition, driving specialization. Plants develop new reproductive strategies relying on wind dispersal and resistant seeds to survive drought. Carnivores diversify their feeding habits, occupying different ecological niches. life on land becomes both more varied and more interdependent than before. The sedimentary record of this world captures its complexity. Layers of red and brown sandstone contain footprints of animals crossing dry floodplains, their tracks preserved by sudden rains. Petrified wood records the growth patterns of forests that endured seasonal stress. Charcoal fragments reveal frequent fire, while fossilized pollen documents the dominance of gymnosperms plants that reproduce by exposed seeds rather than flowers. Together, these remnants portray a biosphere vigorous but precarious thriving under conditions that push its limits. The oxygen-rich air and extensive vegetation create a feedback loop that stabilizes the climate, yet it is a balance maintained by constant flux. As deserts expand and forests retreat, dust increases, influencing atmospheric circulation. As rivers shift course, wetlands dry and new ones form elsewhere. Over time, slow tectonic uplift and erosion reshape drainage systems, altering habitats across entire regions. Despite such changes, life remains resilient. The animals of the Permian world are well adapted to endurance, not abundance. They inhabit a planet of steady but demanding rhythms, a world where survival depends on flexibility more than speed. Toward the close of the Permian, evolutionary innovation reaches a quiet peak. No dramatic explosions of diversity occur, but existing lineages refine their forms. Herbivores grow larger, carnivores more specialized, and plants more efficient at reproduction. The biosphere of Pangea appears stable, its ecosystems widespread and interconnected. Yet beneath this stability, geological and atmospheric processes begin to shift. The volcanic provinces in the northern interior accumulate pressure, and subtle changes in ocean chemistry hint at imbalance. For the living world, these are imperceptible signals. The forests still grow, the rivers still flood, and the synapsids still hunt under the same red skies. But in the layers of rock that will one day tell the story, the warning signs are already being written. The unity of land and life that defines this moment is both culmination and prelude, a thriving surface poised at the edge of profound transformation. Before the world darkens, the seas of the late Permian remain places of abundance and intricate stability. The coastlines of Pangea stretch endlessly, curving through humid deltas, shallow embayments and reef-fringed lagoons. These marginal seas, warmed by equatorial sunlight and nourished by rivers flowing from the mountains of the supercontinent, support ecosystems of remarkable diversity. Coral-like sponges and algae build extensive reefs that shelter countless organisms. Within these reefs live brachiopods, crinoids, mollusks, and the elegant ammonoids whose coiled shells drift through clear water. Shoals of early bony fish glide above the reef slopes, while beneath them the seafloor teems with life-burrowing worms, echinoderms and arthropods stirring sediment in a continuous cycle of oxygenation and decay. This underwater landscape stretches for thousands of kilometers, nearly uninterrupted along the continental shelves of Panthalassa and the Tethys Sea. The clarity of these shallow waters reflects a world in balance. Photosynthetic algae and cyanobacteria convert sunlight into energy-releasing oxygen that sustains marine life. Nutrients carried by rivers from the supercontinent's interior feed this production, but the supply is moderate enough to avoid stagnation. Circulation between surface and deep water, though sluggish compared to modern oceans, is sufficient to renew oxygen in the lower layers. The chemical composition of seawater, its balance of carbon, calcium and sulfate ions, remains within stable bounds, allowing shells and skeletons to form freely. Carbon dioxide from the atmosphere dissolves in the upper ocean, supporting the carbonate cycle that stores carbon in limestone sediments. This equilibrium between gas exchange, biological activity and mineral deposition makes the Permian Ocean both resilient and productive. Along the equatorial coasts, coral reefs and sponge mounds flourish in belts of constant warmth. The organisms that build them live in symbiosis with microscopic algae, their relationship finely tuned to temperature and light. In slightly deeper water, radiolarians and foraminifera drift in great numbers, forming invisible clouds that will later settle to the seafloor as siliceous ooze. Predators patrol the open water sharks, cephalopods, and early marine reptiles, while planktonic larvae disperse with the currents, linking far-flung populations into one continuous marine community. The biodiversity of these seas rivals that of any before or since. In the fossil record, it appears as dense accumulations of shells, corals and carbonate muds, evidence of a biosphere at its peak. In the higher latitudes, cooler waters favour different assemblages. Brachiopods and bryozoans dominate, forming dense mats across the seafloor. Crinoid gardens wave slowly in the currents, filtering microscopic particles from the water column. These colder seas, though less diverse than tropical reefs, remain vital parts of the global ecosystem. Their deep mixing supplies oxygen to the abyssal zones, while their sediments record chemical signatures of a planet still in equilibrium. Yet small changes are underway. Layers deposited in late Permian time show subtle shifts in carbon isotopes, suggesting fluctuations in biological productivity and organic carbon burial. These signals hint at slow transformations in the Earth's carbon cycle, though life continues unaffected for now. The surface of Panthalassa during this period would have appeared serene, vast blue plains, broken only by drifting mats of plankton. Beneath, temperature gradients separate the warm surface layer from the cold, dense depths. This stratification reduces mixing, confining most life to the upper few hundred meters where sunlight penetrates. Deep below, currents flow sluggishly, tracing paths around submarine ridges and trenches. Some basins, particularly those restricted by undersea barriers, begin to show reduced oxygen, their sediments dark and organic rich. These anoxic regions remain localized but foreshadow the more extensive depletion that will one day envelop much of the world ocean. The Tethys Sea, by contrast, is an intricate network of shallow basins and island arcs. Here, warm tropical waters circulate through narrow channels, creating environments of constant change. Salinity varies with rainfall and evaporation, and marine life adapts accordingly. Stromatolites, layered structures built by microbial communities, cover some coastal flats, while shoals of ammonoids move between open water and the reef-fringed margins. The diversity of species in this region reflects both isolation and exchange. Each bay and lagoon hosts unique assemblages, yet all remain connected by the movement of larvae and currents. The Tethys will become a refuge for survival in the ages to come, but in the late Permian, it is still one thriving piece of a global oceanic mosaic. The stability of these ecosystems depends on temperature remaining within narrow limits. A few degrees of warming or cooling can alter the solubility of gases in seawater and the distribution of nutrients. Geological evidence suggests that during the late Permian gradual warming occurs driven by slight increases in atmospheric carbon dioxide. This warming is gentle, at first extending growing seasons and expanding tropical zones. Coral reefs migrate poleward, and evaporation from the sea surface intensifies, feeding stronger monsoons along Pangea's coasts. These changes seem benign, even beneficial. Life adjusts as it has through previous cycles, unaware that the slow accumulation of heat carries consequences not yet visible. The sedimentary archives of this time hold more clues to the balance of the ocean. In some regions, thin layers of volcanic ash appear among marine limestone's remnants of distant eruptions that scattered fine particles across the sea. These events fertilize surface waters with trace elements temporarily boosting productivity. Each pulse of growth draws carbon from the atmosphere, lowering temperatures slightly, only to be followed by a rebound as decay releases it again. The Earth's systems continue to oscillate around equilibrium, finely balanced by feedbacks between biology and geology. But balance does not guarantee permanence. As the late Permian advances, subtle disruptions accumulate. Increased weathering of continental rocks alters the flow of nutrients into the sea. Oxygen levels in the deep ocean fluctuate more widely, sometimes dropping enough to stress sensitive organisms. In the fossil record, this appears as a gradual decline in certain species of corals and brachiopods, even as others persist. No single event marks the change, only a quiet erosion of diversity that hints at the vulnerability of complex ecosystems. For now, the oceans still sustain the rhythm of life. Waves lap against the coasts of Pangea, carrying the sound of stability that has lasted for tens of millions of years. The great gyres of Panthalassa move unhurriedly, their flow guided by the shape of the supercontinent. The winds that drive them rise from deserts and forests, completing the global circuit of energy. Sunlight flashes off the crests of waves, illuminating plankton that drift like dust in air. The scene is tranquil, the equilibrium deep. Yet the very processes that maintain this calm, the slow circulation, the build-up of nutrients, the gentle rise of temperature are preparing the conditions for collapse. When the balance tips, it will do so everywhere at once, uniting the planet's waters in crisis. For now, the ocean holds its breath, vast, blue, and deceptively still. In the final chapters of the Permian world, the calm that has long defined Earth's oceans and continents begins to shift in ways that at first seem minor. The sediments that settle quietly across the seafloor record these changes long before they become visible at the surface. Chemical signatures preserved within fine layers of mudstone and limestone reveal a slow alteration in the balance of carbon and oxygen circulating through the planet's systems. Ratios of isotopes within marine carbonates suggest that less carbon is being buried as organic matter, meaning that more remains in the atmosphere. This subtle rise in atmospheric carbon dioxide begins to amplify temperatures, affecting evaporation, rainfall, and ocean currents. At first, the warming is modest, but even small increases ripple across the interconnected systems of land, air, and sea. In shallow marine environments, corals and sponges that once flourished start to decline. Reefs that had extended for kilometers along Pangea's coast show gaps where growth ceases and erosion takes over. The loss is gradual enough to escape notice in the fossil record until whole reef systems disappear within a few geological layers. These collapses coincide with evidence for oxygen depletion in bottom waters. Sediments deposited during this time become darker, richer in organic material, and lacking in bioturbation, the marks left by burrowing animals. In places where the sea once teemed with life, the mud now settles undisturbed, the quiet signature of an ocean losing breath. On land, the signs of imbalance are equally subtle. Fossil pollen and spores show shifts in vegetation patterns, with some plant species retreating toward wetter coastal zones and others expanding into the interior. Droughts become longer and more frequent as the monsoon system weakens. Rivers that once fed fertile floodplains begin to fluctuate in volume, alternating between violent floods and prolonged dry intervals. The soil chemistry of these regions records the stress layers of caliche, hardened by evaporation form, where moisture once sustained continuous plant growth. The combination of rising heat and decreasing rainfall gradually transforms much of the interior into desert. Geological evidence suggests that this environmental stress is not random. Deep within the crust, immense volcanic provinces begin to awaken. The first pulses of magmatic activity occur in what will become Siberia, releasing gases rich in carbon dioxide and sulfur compounds. These eruptions, though initially localized, inject enormous quantities of gas into the atmosphere. Over thousands of years, the accumulation of these emissions begins to change the planet's climate on a global scale. Sulfur aerosols reflect sunlight, cooling the surface temporarily, while carbon dioxide traps heat for far longer periods. The alternation between short-term cooling and long-term warming destabilizes the climate, confusing the established cycles of monsoon and drought. In the oceans, this instability becomes visible as a pattern of fluctuating oxygen levels. When surface waters warm, they become less dense and less able to mix with the cooler layers below. The deep sea, already sluggish in circulation due to the configuration of Panthalassa, loses oxygen more rapidly. As the oxygen declines, microbial communities shift toward those that can tolerate or even thrive in low oxygen conditions. These organisms release hydrogen sulfide, a toxic gas that reacts with metals in the sediment to produce black iron sulfides. The resulting dark layers, still visible in rocks today, trace the gradual suffocation of the ocean. In some basins, fossils show signs of stress. Thin shells, smaller body sizes, and reduced diversity reflecting conditions near the limit of habitability. The feedback between ocean and atmosphere grows stronger as these processes continue. Warm water holds less gas, reducing oxygen solubility further. Carbon dioxide released by volcanism dissolves into seawater, forming carbonic acid that lowers pH and makes it harder for marine organisms to form shells. Coral reefs weaken, carbonate deposition slows, and chemical buffering decreases. The oceans become more acidic, eroding the very structures that once stored carbon in solid form. This self-reinforcing cycle leads to gradual but irreversible change. On land, life adapts as best it can. Therapsids. The dominant vertebrates diversify into many forms, some small and nocturnal, others large and herbivorous. Their fossils show evidence of high metabolic rates and advantage in fluctuating climates. Yet even these resilient creatures face dwindling resources. Vegetation declines as drought spreads, reducing available food. Fires once seasonal become nearly continuous across parts of the interior. Charcoal layers in late Permian sediments reveal a world burning more often than regrowing. The combination of heat dryness and poor soil quality turns large regions into wastelands. The polar regions, once cool and relatively stable, begin to warm as well. Ice remnants in the southern hemisphere retreat entirely, leaving behind valleys carved by ancient glaciers. As reflective ice vanishes, more sunlight is absorbed by dark rock and ocean water, reinforcing the warming trend. The global temperature gradient flattens, weakening the planetary wind systems that once distributed heat evenly. Without strong circulation, stagnant air pools over the continents, trapping dust and heat. Deserts expand northward and southward, connecting across the equator in a continuous belt. The changes in ocean chemistry can be traced through isotopic records preserved in carbonate rocks worldwide. Sharp fluctuations in carbon isotope ratios suggest that vast amounts of carbon are being released into the atmosphere faster than biological or geological processes can absorb it. The source may be volcanic, but it may also include methane released from seafloor sediments as temperatures rise. Methane, a potent greenhouse gas, accelerates the warming, pushing the planet into a feedback loop that becomes increasingly difficult to reverse. In the fossil record, these years appear compressed into a thin layer of transition. The shift from stable oxygen-rich sediments to dark, organic-rich shales marks the threshold between two states of the Earth system. In this brief geological interval, the complex equilibrium of the Permian biosphere begins to falter. Coral reefs vanish, shallow marine communities collapse, and terrestrial ecosystems fragment. Yet to an observer living at the time, the changes might still seem slow. The forests still grow in the wet seasons, the rivers still reach the sea, and the winds still move across the deserts. It is only in the accumulating layers of rock and in the chemistry of the oceans that the warning becomes clear. By the close of the Permian, the planet stands on the brink of transformation. The air holds more carbon, the seas hold less oxygen, and volcanic activity in the north intensifies. Earth's systems, interconnected and once self-correcting, begin to feed upon their own instability. What follows will not be a single moment, but a cascade as the planet's balance gives way to a new and unfamiliar state. For now, the signals of disturbance remain subtle, a darker layer in the ocean mud, a change in the shells of small creatures, a shifting pattern of winds, but they mark the silent arrival of a crisis that will soon encompass the entire globe. In the geological record, the transition between the Permian and Triassic periods appears as a line no thicker than a hand. Yet within that narrow band lies the greatest loss of life the planet has ever endured. Roughly 252 million years ago, the stability that had governed Earth for millions of years collapses in a chain reaction that affects every corner of the biosphere. The supercontinent of Pangea remains where it was, but the forces beneath and above it act with unprecedented intensity. Massive volcanic eruptions in the region now known as Siberia expel immense volumes of magma and gas over an interval of less than 1 million years. Lava floods cover an area larger than modern Europe, building layers of basalt several kilometers thick. Each eruption releases carbon dioxide, methane, sulfur dioxide, and water vapor into the air. The result is both rapid warming and short-lived cooling, an atmospheric oscillation that the planet's systems cannot absorb. Sulfur aerosols reflect sunlight, plunging regions into temporary darkness, and causing acid rain that leaches nutrients from the soil. Meanwhile, carbon dioxide accumulates over longer timescales, driving global temperatures upward. Estimates suggest that the mean surface temperature rises by several degrees and ocean waters follow. The warming reduces the solubility of oxygen, further depleting what little remains in the deep sea. As circulation weakens, anoxic zones expand across Panthalassa and the Tethys Sea. In these oxygen-starved basins, hydrogen sulfide gas begins to build, produced by sulfate-reducing bacteria that flourish in the absence of oxygen. When upwelling or storms bring these toxic waters to the surface, entire marine ecosystems suffocate almost instantly. The collapse is total in scope. Coral reefs already weakened by warming and acidification vanish. Brachiopods, which had dominated the seafloor for hundreds of millions of years, disappear almost entirely. Trilobite survivors of earlier extinctions finally die out. Ammonoids, crinoids, and countless species of mollusks and plankton follow. More than 9/10 of marine species are lost, along with most of the complex reef-building communities that had structured marine life. In the sediments of this time, fossil layers thin and then cease. Dark shales replace limestone, recording a world where oxygen no longer reaches the ocean floor. On land, the devastation is just as profound. Forests burn and fail to return. Pollen and spores in rock layers show an abrupt decline in diversity, replaced by traces of fungal growth that thrive on decaying matter. Rivers fill with ash and sediment, clogging floodplains. Insects once abundant suffer heavy losses. Amphibians and large reptiles vanish from entire regions. The great therapsids, masters of the late Permian, dwindle to a few surviving lineages. Even the hardier species find no refuge, for the crisis is global. Temperature extremes exceed tolerance limits. Drought alternates with sudden floods, atmospheric oxygen falls to its lowest levels in hundreds of millions of years. The air becomes thin and stifling, and animals adapted to high metabolism struggle to breathe. The cause of this sequence lies in feedback between the planet's systems. As volcanic gases warm the surface permafrost and methane hydrates in seafloor sediments destabilize, releasing methane, a greenhouse gas far more potent than carbon dioxide. The surge of heat that follows accelerates chemical reactions on land-drying soils and increasing erosion. With vegetation gone, carbon that had been stored in organic matter enters the air. Acid rain dissolves minerals from rocks, sending nutrients into rivers, and then into the ocean where they fuel blooms of algae. The decay of this organic matter consumes more oxygen, spreading anoxia further. Each step amplifies the next, a cascade of reinforcement that no natural mechanism interrupts. For marine life, the loss of oxygen is decisive. Creatures that rely on continuous respiration, fish, mollusks, and most invertebrates succumb first. Those that tolerate low oxygen, such as certain bacteria and plankton, expand, rapidly altering ocean chemistry further. Hydrogen sulfide accumulates in surface waters and escapes into the atmosphere, forming a thin veil of toxicity. When this gas reacts with sunlight, it erodes the ozone layer, exposing the planet to increased ultraviolet radiation. The combination of heat, acid rain, and radiation sterilizes large areas of land and sea. The planet does not burn or freeze, it suffocates. Geological evidence of this interval is strikingly consistent across continents. At the boundary layer, carbon isotope values plunge, signaling a massive injection of light carbon into the atmosphere, likely from volcanic and methane sources. The same pattern appears in rocks from China, South Africa, Greenland, and Western North America, confirming that the change is global rather than regional. Beneath the microscope, fossilized plankton shells show signs of dissolution, a result of acidified water. Above this layer, sediment becomes barren of complex life for tens of thousands of years, the so-called coal gap, in which forests cease to produce the peat that forms coal. The temperature gradient between equator and poles nearly vanishes, erasing climatic diversity. Deserts spread to the coasts while polar regions warm into temperate zones. Rain patterns collapse as atmospheric circulation weakens. The world's surface becomes uniform in its misery-humid heat. Near the oceans, desiccation inland and lifeless calm in between. In this transformed landscape, survival is rare. A few small synapsids and reptilian lineages endure by sheltering in burrows or along waterways. In the ocean, microbial mats replace coral reefs, and a handful of resilient ammonoids drift in the upper layers. The total loss of biodiversity is staggering. Estimates suggest that nearly all marine species and most terrestrial ones vanish, reducing life's complexity to a fraction of its former state. The biosphere, which had once extended into every ecological niche, shrinks into scattered enclaves. Evolution slows to a crawl as ecosystems simplify. Food chains collapse to single tiers of survivors feeding on microbial productivity. For millions of years after recovery will proceed painfully slowly. The Earth itself bears scars beyond biology. Vast basalt plains in Siberia mark where magma once erupted through the crust, their extent covering millions of square kilometers. The gases released carbon dioxide, methane, sulfur, chlorine alter the atmosphere permanently. The thin soils that remain on the surface turn saline, and rainfall leaches them into the sea, further disrupting chemistry. Ocean circulation, already sluggish, nearly stops. Temperature differences between surface and depth diminish until the ocean becomes a stratified, stagnant body. For a time, even the deep waters warm an unprecedented condition that ends the last refuges of life. The planet, once vibrant with forests and coral reefs, enters a state of near silence. For thousands of years, the noise of animals and the rustle of vegetation vanish from large regions. Volcanoes continue to erupt. The sky glows red with haze and acidic rain falls on bare rock. Yet beneath the devastation processes of renewal begin quietly. Microbes in the sea adapt to the new chemistry, pioneering metabolic pathways suited to low oxygen. On land, a few plants capable of surviving in nutrient-poor soil take root. The great dying, though total in appearance, is not the end but the contraction before recovery. Still, for those who lived within it, had any eyes remained to see, the earth would have seemed still and alien, a planet of dust, heat and darkness, holding only the memory of its former abundance. Deep within the earth, the roots of catastrophe lie not in the atmosphere or the ocean, but in the restless circulation of the mantle itself. Beneath what is now Siberia, a vast plume of molten rock rises from the boundary between core and mantle, a column of heat that has been gathering energy for millions of years. As it approaches the base of the crust, pressure forces magma upward, fracturing rock and releasing volcanic gases through innumerable vents. The eruptions that follow are not brief explosions, but sustained floods of lava that last for hundreds of thousands of years. These outpourings build the immense basalt province known today as the Siberian Traps. The term traps, from the Scandinavian word for stairs, describes the terraced layers of solidified lava that step across the landscape for hundreds of kilometers each tier, representing a separate pulse of eruption. Together, these flows form a province covering more than 5 million square kilometers and reaching several kilometers in thickness, one of the largest volcanic events in planetary history. The energy released is incomprehensible. Each eruptive phase disgorges trillions of tons of molten rock, along with gases that alter the composition of the atmosphere. Carbon dioxide emerges in vast quantities, enough to increase greenhouse forcing across the entire planet. Sulfur dioxide rises too, forming reflective aerosols that temporarily cool the surface, but later fall as acid rain. Hydrogen chloride and fluorine gases add their own corrosive influence, dissolving into precipitation that sterilizes soil and lakes. The alternating effects of short-lived cooling and long-term warming unsettle every part of the climate system. Ocean currents shift, wind belts falter, rainfall becomes erratic. On geological timescales, this period of eruption is brief, yet its impact lasts for millions of years. Below the visible flows, even greater changes occur. As magma intrudes into thick layers of sedimentary rock rich in organic matter and evaporates, it triggers massive contact metamorphism. The heat and chemical reactions release additional gases, carbon dioxide, methane, and halocarbons. These compounds, liberated from buried carbon reservoirs, multiply the greenhouse effect, already driven by volcanic emissions. Methane especially traps heat with extraordinary efficiency. Each pulse of eruption thus generates not only lava, but a surge of atmospheric transformation. The cumulative warming from these feedbacks pushes global temperature several degrees higher than it had been even at the height of the Permian's natural warmth. The structure of the mantle plume contributes to the persistence of this activity. Unlike localized volcanoes that vent pressure through a single conduit, this Siberian system spreads across hundreds of fractures, allowing continuous release. Between eruptions, lava lakes and shallow magma chambers simmer just below the surface, leaking gases into the air. The basalt itself cools, slowly releasing steam and carbon dioxide long after the main flows cease. Even when active eruption stops, the landscape continues to fume. For centuries after each pulse, the air is thick with haze. Acidic rains fall across continents and rivers carry dissolved minerals into the oceans, altering their chemistry further. The thermal pulse from this magmatism disturbs the deep crust as well. The heat weakens surrounding rock, increasing the likelihood of additional fracturing and outgassing. Volcanic ash and aerosols spread across the globe recorded today as thin layers of glassy minerals in distant sedimentary basins. These ash beds allow geologists to trace the sequence of eruptions with remarkable precision. Radiometric dating shows that the peak of this activity coincides closely with the main extinction interval, confirming that the two events are linked. Yet the connection is not one of instant cause and effect. The eruptions act as the catalyst for a cascade of interactions among Earth's systems, chemical, thermal, and biological, that unfold over thousands of years. The atmosphere becomes dense with greenhouse gases, and global mean temperature rises dramatically. Polar regions warm until ice disappears entirely, while equatorial seas approach temperatures lethal to most marine life. Ocean circulation, already slowed by the geometry of Pangea, weakens further as the temperature gradient between poles and tropics flattens. Stagnant water layers trap heat and limit oxygen exchange. As warm oxygen-poor conditions expand, sulfate-reducing bacteria proliferate, releasing hydrogen sulfide that poisons marine ecosystems and leaks into the air. This gas in turn reacts with sunlight to erode the ozone layer, allowing ultraviolet radiation to reach the surface unchecked. The synergy between deep magmatism and atmospheric chemistry thus converts the planet's internal energy into global environmental collapse. On land, the geological consequences are equally severe. Earthquakes accompany the spreading of magma shaking the continental crust. Groundwater systems are disrupted. Volcanic ash settles across entire regions, suffocating vegetation. Rivers run black with sediment. The injection of dust and aerosols temporarily dims the sun, lowering photosynthesis before warming reasserts dominance. The oscillation between these extremes darkened skies, followed by blazing heat, destroys the predictability upon which ecosystems depend. Forests vanish under alternating frost and fire. Acid rain leaches essential nutrients such as calcium and potassium from the soil, leaving it barren. The decomposition of organic matter under heat releases still more carbon dioxide, a final echo of the magmatic emissions that started the cycle. From a planetary perspective, the Siberian traps act as a vent for internal heat, accumulated over eons. Mantle plumes of similar scale have occurred before and after, but rarely have they coincided with continental configurations that amplify their effects. The position of Pangea concentrates weathering and runoff in limited regions, restricting the planet's ability to draw down carbon dioxide. At the same time, the unified landmass ensures that atmospheric circulation spreads volcanic gases uniformly across both hemispheres. The result is a warming that is global rather than regional, transforming every environment at once. In the deep subsurface, the remnants of these eruptions remain as thick sheets of basalt interlayered with altered sediments. Analysis of trapped gases in these rocks shows evidence of the chemical reactions that drove the crisis: carbon isotopes that record massive degassing and mineral veins filled with sulfates formed from acid-rich fluids. These geological archives confirm that the Earth's greatest extinction was rooted not in external impacts or celestial accidents, but in the planet's own internal dynamics. The mantle's convective power, acting through the slow mechanics of plate tectonics, became the ultimate architect of extinction. After the main eruptions cease, their influence persists for millennia. The atmosphere remains rich in carbon dioxide, keeping temperatures elevated even as the sky clears. The basalt plains, still warm from residual heat, emit steam and gas long after solidification. Chemical weathering of the new rock draws down carbon, slowly, a process that will eventually help restore balance but only after millions of years. During this prolonged aftermath, life begins its slow return. Microbes colonize the volcanic terrain, first feeding on minerals released from the fresh rock. In the oceans, photosynthetic plankton gradually reappear where sunlight penetrates the upper layers. Yet the recovery is hesitant, constrained by continued instability in climate and chemistry. The forces beneath the surface thus define both the destruction and the foundation for renewal. They demonstrate the scale at which the planet operates, where geological time and biological time intersect in events that transform the entire biosphere. The Siberian traps, silent now and eroded by ages, still mark the memory of that boundary, when the Earth exhaled its interior and life nearly ceased. The connection between the deep mantle and the thin skin of life above it remains one of the planet's enduring truths. The processes that sustain existence can also, under different conditions, bring it to the brink of disappearance. When the eruptions wane, the consequences of their gases remain. The atmosphere that envelopes the supercontinent is no longer the same medium that once sustained forests, insects, and reptiles. Carbon dioxide concentrations climb to levels far beyond the capacity of plants or oceans to absorb, while oxygen levels fall to nearly half of what they once were. The chemistry of air, sea, and soil now functions as a single, interconnected system of imbalance. Heat retained by the thickened greenhouse drives the surface temperature upward, raising average conditions across the planet until tropical zones expand toward the poles. Oceans warm in response, and the circulation that once distributed oxygen through the depths slows to near stagnation. The sea surface grows calm and dense, isolating the deep basins where microbial activity consumes what oxygen remains. The global ocean, once a continuous engine of life, becomes a layered body of suffocation. As this process unfolds, the interaction between air and water produces a feedback that accelerates collapse. Warm water holds less gas, so as temperatures rise, oxygen solubility declines further. Decomposition of dying plankton adds carbon dioxide to the water column, increasing acidity. Calcium carbonate, the mineral foundation of shells and reefs, begins to dissolve. Coral sponge and mollusk skeletons weaken and crumble. The sea that once offered refuge during earlier crises becomes an environment of dissolution. At the surface, blooms of algae feed on the influx of nutrients from eroding land and volcanic ash. When these blooms die, bacteria decompose the organic matter, consuming still more oxygen and releasing hydrogen sulfide. This gas rises through the layers, forming a toxic boundary that spreads across continental shelves. In some regions, upwelling currents bring it to the surface, releasing it into the atmosphere, where it reacts with sunlight and further degrades the protective ozone layer. Ultraviolet radiation increases, damaging the DNA of surviving organisms on land and in shallow seas alike. The soil of Pangea's landmass endures a parallel transformation. Without vegetation to anchor, its topsoil erodes under the assault of torrential rain, and later by wind. Rivers carry enormous loads of sediment into the ocean, clouding coastal waters and smothering remaining reefs. The nutrients released by this erosion stimulate further algal growth, completing a destructive cycle between land and sea. Acid rain generated from volcanic gases and atmospheric reactions leaches essential minerals from the ground, stripping away fertility. The fine dust that replaces soil reflects sunlight, temporarily cooling regional climates, but doing nothing to reverse the overall warming trend. In some basins, thick layers of evaporate minerals form as standing lakes dry completely, leaving only salt plains where once there were forests. The atmosphere, altered in composition, exerts a profound effect on living organisms. With oxygen diminished, respiration becomes difficult even for those species that survived the initial catastrophe. Animals retreat to lowlands and caves where cooler and slightly denser air offers a marginal advantage. Some small therapsids and reptiles endure by slowing their metabolism, reducing activity during the heat of the day. On the open plains, the combination of high temperature and low oxygen renders large body sizes unsustainable. Evolution temporarily favors the small, the burrowing, and the nocturnal. Plant life fares no better. Many lineages disappear altogether. Those that remain are sparse and stunted. Conifers survive in limited patches near the coasts, while opportunistic ferns recolonize disturbed ground after brief wet seasons. The fossil record of this interval shows a dominance of spores rather than seeds, indicating ecosystems reverting to simpler, more ancient forms of vegetation. The physical appearance of Earth changes in step with these processes. The supercontinent's deserts spread outward, their red sands covering the remnants of river valleys. Dust storms rise and cross what were once mountain forests, carrying fine grains thousands of kilometers before settling over the sea. The sky takes on a pale copper hue from the scattering of particles and aerosols. Rain becomes infrequent and acidic, falling in bursts that erode rather than nourish. Lightning ignites dry vegetation, but the fires burn slowly under oxygen-poor air, producing heavy smoke that lingers for months. Nights are warm and windless, the heat radiating upward, only to be trapped again by the dense blanket of carbon gases. The ocean's chemical equilibrium reaches a breaking point. As hydrogen sulfide continues to rise from the depths, it interacts with the atmosphere to form compounds that contribute to further greenhouse warming. Some models suggest that entire portions of the ocean turn anoxic to depths of several kilometers. The normally dark seafloor becomes layered with fine black mud rich in sulfur minerals. These deposits, later compressed into rock, preserve the signature of chemical reactions that occurred in the absence of life. Within these sediments, the microscopic shells of plankton vanish, replaced by amorphous carbon residues left by decaying organic matter. The deep ocean, once a realm of slow but steady circulation, becomes a silent sink of decomposition. Volcanic activity, though diminished, still releases gases through fissures scattered across the basalt plains. Each emission reinforces the disequilibrium, maintaining high temperatures even as the initial eruptions end. The combination of stagnant air and continuous outgassing leads to climatic uniformity across latitudes. Polar regions, no longer cool enough to form ice in equatorial zones, experience heat that pushes beyond the tolerance of most complex organisms. With the temperature gradient flattened, global wind systems weaken, reducing evaporation and further disrupting rainfall patterns. The world becomes motionless in its imbalance, an atmosphere heavy with moisture that rarely condenses, an ocean warm yet deprived of oxygen, and a land stripped of green. The biosphere's collapse transforms the carbon cycle itself. Decomposition slows in oxygen-deprived environments, causing carbon to accumulate in dissolved form, rather than locked in solid minerals or organic tissues. This excess carbon continues to circulate between atmosphere and ocean, prolonging the greenhouse state. The processes that normally stabilize climate, rock weathering, biological uptake, burial of organic matter, are too weakened to function effectively. It will take millions of years before erosion of the new basalt formations begins to draw carbon dioxide from the air through chemical weathering, gradually restoring balance. Until then, Earth remains caught in a feedback loop of warmth and suffocation. Yet even amid devastation, subtle processes of resilience begin. In isolated freshwater pools and coastal shallows, microbial mats re-emerge, forming thin films that trap sediment and begin rebuilding soil. These communities of cyanobacteria and algae endure the extremes of temperature and radiation, slowly releasing oxygen back into the air. On land, hardy species of ferns and conifers recolonize the periphery of the volcanic provinces, taking advantage of mineral-rich ash deposits. Insects return first small and wingless, followed by amphibians in cooler regions where humidity lingers. These pioneers mark the earliest stages of recovery, but their presence does not yet alter the overwhelming conditions of heat and toxicity. The planet remains largely barren, its rhythms slowed almost to stillness. The crisis of air, sea, and soil reveals the fragility of interconnected systems that sustain life. When one falters, the others follow, cascading into a state from which only time can rescue the planet. In the Permian's aftermath, the Earth becomes a laboratory of endurance. For tens of millions of years, its surface will carry the memory of the imbalance: black shales on the ocean floor, red deserts on the continents, and a sky forever changed by the gases that once escaped from the deep. The world survives, but only barely, waiting in silence for the slow repair that will lead to the dawn of the Triassic. When the heat finally begins to fade, the Earth is quiet. The supercontinent still stretches across half the globe, but the colour of its surface has changed. The once green coastlines and forested uplands are now bands of ochre tan and blackened basalt. The air, though still heavy with carbon dioxide, clears enough for sunlight to return in its full brightness. Over the next several million years, this light becomes the energy source for a hesitant revival. The recovery of life after the Great Dying is not swift. It proceeds in slow waves, each one rebuilding the planet's system step by step. The first organisms to reclaim the devastated landscapes are microscopic bacteria, algae, and fungi adapted to the high temperatures and unstable chemistry. On the continents, these microbes form dark crusts on the bare rock, stabilizing surfaces against erosion. In shallow pools left behind by evaporated lakes, cyanobacteria flourish, producing thin mats that generate oxygen. Over time, these simple communities help re-establish the processes of weathering and soil formation that more complex life depends upon. In the oceans, a similar reawakening occurs. For thousands of years after the extinction, the waters remain stratified and largely anoxic. Gradually, as volcanic activity wanes and rainfall resumes, erosion of new basaltic rocks draws carbon dioxide from the atmosphere. The cooling that follows allows ocean currents to strengthen again. Slowly, oxygen penetrates deeper into the water column. The black muds of the seafloor give way to lighter sediments as the chemistry shifts toward recovery. Plankton populations begin to increase, feeding on nutrients supplied by rivers from the rejuvenated land. Their photosynthesis restores oxygen to the surface layers, setting in motion the first hints of a balanced carbon cycle. On land, vegetation takes longer to return. The earliest plants to reappear are ferns and lycophyte species that spread through spores and can grow in disturbed soils. Their short life cycles allow them to colonize areas quickly after rains. These pioneer plants trap dust and ash, forming the first fragile soils of the Triassic world. Gradually, conifers follow their roots, stabilizing riverbanks and slopes. In the lowlands, cycads and seed ferns begin to dominate, their tough leaves suited to heat and drought. The forests of the Permian do not return. Instead, a new kind of vegetation emerges, simpler, more tolerant of extremes but capable of enduring. Over time, this plant cover rebuilds the atmosphere, reducing carbon dioxide and increasing oxygen once again. The recovery of animal life mirrors this cautious progression. The few lineages that survived the extinction diversified to fill empty ecological niches. Among them are small lizard-like reptiles that evolve into new forms adapted to the altered environment. Insects reappear in parallel, their wings and exoskeletons evolving to withstand higher ultraviolet radiation. Amphibians return to rivers and lakes, though far less diverse than before. The dominant survivors on land are the therapsids whose evolutionary flexibility allows them to persist through scarcity. Some species remain small and nocturnal, while others develop upright postures and more efficient metabolism. These changes mark early steps toward the true mammals that will come much later. In the seas, recovery unfolds in cycles of expansion and collapse. Early Triassic oceans remain unstable, with oxygen levels fluctuating for millions of years. After each improvement, another warming episode or volcanic pulse sets conditions back. Marine ecosystems rebuild from microbial mats upward. Thin carbonate layers formed by simple shell-building organisms alternate with dark shales that signal recurring anoxia. Gradually, ammonoids and bivalves diversify again, followed by the appearance of new groups of fish. Coral reefs do not return immediately. Instead, sponge reefs take their place, creating modest structures that shelter small communities of invertebrates. It will be many millions of years before complex coral reefs once again encircle the continents. The pace of biological innovation quickens as stability returns. In the mid-Triassic, ecosystems on land and sea begin to reorganize into new forms. The boundaries that had defined Permian life between reptile and mammal, between amphibian and reptile, between land and sea, blur as evolution experiments with new solutions. Archosaurs, a group that includes the ancestors of dinosaurs, crocodiles and birds arise during this time, exploiting open habitats left vacant by extinction. Their limb posture and efficient lungs give them advantages in the oxygen-poor atmosphere. At the same time, the ancestors of modern conifers and cycads spread across the warming continents, establishing forests that stabilize climate and promote rainfall. By restoring carbon exchange between vegetation and atmosphere, these new ecosystems reweave the planetary fabric of life. Geological evidence of recovery is preserved in sedimentary layers that record alternation between barren intervals and renewed growth. Early Triassic strata are thin and sparse with few fossils. Above them, younger layers show increasing organic content and diversity of forms. Trace fossils, footprints, burrows, feeding marks appear before abundant skeletal remains, indicating that behavior re-emerges before complexity. The return of large animals follows only after ecosystems can once again support them. It is a slow but cumulative process stretching across 10 million years before diversity begins to approach pre-extinction levels. The chemistry of the planet stabilizes in parallel. As fresh basalt weathers under tropical rains, it reacts with carbon dioxide to form carbonate minerals, locking carbon into rock. This process cools the climate further, breaking the long greenhouse cycle that began with the Siberian eruptions. Oceanic circulation strengthens as temperature gradients reappear between poles and equator, restoring the global oxygen supply. The deep basins of Panthalassa and the Tethys Sea, once stagnant, become active again, allowing complex life to recolonize the abyss. With each passing epoch, the planet breathes a little easier. The landscape of the recovering world, however, remains strange. Pangea's vastness still dominates, creating inland regions with arid climates and strong seasonal contrasts. The new forests cluster along rivers and coasts, while deserts persist across the continental interior. The combination of open plains and intermittent rainfall favors the evolution of animals adapted for movement and endurance. The fossil record of the Triassic reveals footprints of agile reptiles and early mammal relatives crossing dried mudflats, signs of a biosphere that has regained both energy and adaptability. Despite the return of life, the memory of catastrophe remains imprinted in the rocks. The boundary between Permian and Triassic strata is unmistakable, an abrupt transition from fossil-rich limestone to barren shale, from bright marine colors to dark sulfur-stained layers. Above it, the signs of recovery are incremental and patient. Each bed of sediment records the slow reassembly of ecological complexity. The absence of coal for millions of years after the extinction known as the Coal Gap reminds geologists that forests took far longer to regenerate than animals did. The planet's renewal was measured not in years or centuries, but in entire geological ages. By the middle of the Triassic, the atmosphere stabilizes at higher oxygen levels, the seas clear, and biodiversity begins to flourish again. New groups of corals, ammonoids, fishes, and reptiles fill the oceans, while terrestrial ecosystems evolve into modern forms. Life's rebound confirms the resilience of the biosphere, but it also underscores its dependence on geological stability. The same internal forces that nearly erased life will later shape continents, oceans, and climates again, though never with quite the same ferocity. The Earth endures, but each recovery carries the memory of what was lost. The Triassic dawn that follows the Great Dying is a new beginning built on the ashes of an earlier world, a testament to both the fragility and the persistence of life on a planet that continues to change beneath its own unending sky. As life slowly reclaims the surface, the Earth beneath Pangea remains in motion. The mantle that once delivered the vast volcanic plumes of the Siberian traps continues its slow circulation, shifting heat and pressure across the base of the continents. The supercontinent, though seemingly solid, begins to feel the pull of forces that never cease. Beneath the crust convection, currents move in complex patterns, some descending, some rising, and where they diverge, tension forms. Over millions of years, these deep movements create zones of weakness in the lithosphere, initiating the earliest signs of rifting. The surface response is subtle. Long valleys sink and stretch, ancient mountain belts crack under new stresses, and fault lines cut across regions that have been stable since the Permian. These invisible movements mark the beginning of the end for the unified land. The pattern of strain spreads slowly across the continent, first appearing near the margins of the Tethys Sea, and along the western edges facing Panthalassa. Here the crust thins and warps, producing subsiding basins that begin to collect sediments. Rivers adjust their courses, draining into these new depressions, carrying sand and silt that form the first layers of Rift Valley deposits. In places where the crust pulls apart most strongly, volcanic activity resumes not the catastrophic eruptions of earlier ages, but steady outpourings of basalt that trace the fractures like molten handwriting on the planet's skin. These rift-related eruptions vent gases into the atmosphere, though not in volumes capable of disturbing global climate. Instead, they mark a new phase in Earth's tectonic rhythm, the transformation of compression into extension. Over geological time, the distribution of continents and oceans determines how heat escapes from the planet's interior. With Pangea covering so much of the surface, the crust beneath it insulates the mantle below, trapping thermal energy. This buildup of heat eventually weakens the lower lithosphere, making it buoyant and prone to rise. The result is domming of the continental crust, followed by fracturing as the surface stretches to accommodate uplift. In regions such as what will become the Central Atlantic, this process begins quietly during the Triassic, forming broad swells and depressions that alternate across thousands of kilometers. The stress creates linear fault zones and grabens elongated troughs where the crust has sunk between parallel fractures. These features are precursors to the oceans that will later divide the supercontinent. The evidence of this renewal of tectonic activity remains visible today in the geology of the surrounding continents. Thick sequences of red sandstones and conglomerates deposited in arid rift valleys mark the early stages of breakup. Within them lie traces of fluctuating lakes and ephemeral rivers that occupied these basins during wetter intervals. Fossil footprints preserved in these sediments record the movements of early reptiles and amphibians across mudflats shaped by tectonic subsidence, each step pressed into the ground of a continent slowly coming apart. Volcanic dikes and sills intrude these strata, injecting molten rock into cracks that formed as the crust stretched. Many of these features align along directions that will later define the Atlantic Ocean's boundaries. As the mantle continues to convect zones of subduction around Panthalassa, reorganize, dragging parts of the supercontinent's margins downward while pushing others upward. Mountain ranges rise where compression persists, especially along the eastern edge of what will become Asia, while other regions sink beneath the strain of extension. The interplay between uplift and subsidence redistributes erosion and sedimentation across the landmass, altering drainage patterns and regional climates. Rainfall, once governed by monsoon systems centered on a single supercontinent, becomes more localized as topography diversifies. Valleys channel moist air inland, creating new ecological corridors. The climate of Pangea's interior remains largely arid, but along the growing rift zones, volcanic soils and intermittent lakes provide habitats for evolving species. These landscapes, unstable yet fertile, become the testing grounds for the ecosystems that will dominate the Mesozoic world. The mechanical stresses of rifting also influence the deep crust. As faults slip and fractures propagate, magma ascends through the weakened lithosphere, forming networks of intrusive bodies that solidify into gabbro and diabase. These rocks, now exposed in cliffs and mountain ridges, preserve the geometry of the rift system in 3 dimensions. Radiometric dating shows that many of these intrusions formed almost simultaneously across distant regions, evidence that the forces driving breakup were global rather than local. The coincidence of these events with the end of the Triassic suggests that mantle dynamics, not surface erosion or isostatic rebound, provide the primary mechanism. The supercontinent's fragmentation thus emerges as the continuation of the same internal energy that once joined it together. As extension progresses, new basins open to form shallow seas. These waters, fed by rain and groundwater, accumulate salt as evaporation exceeds inflow, producing thick evaporate deposits. Over time, these rift basins deepen enough to admit marine incursions from the Tethys or Panthalassa, transforming lakes into narrow arms of the ocean. Sediments deposited in these early marine environments record alternating layers of red sand, grey mud, and white salt, each representing shifts between terrestrial and marine conditions. These sequences form the foundation of future continental margins and mark the birthplaces of the oceans that will one day encircle separate continents. The biological world, now fully engaged in recovery, adapts to the changing geography. Reptiles diversify into forms suited to the evolving landscape's agile predators that roam the arid plains, aquatic species that inhabit the new rift lakes, and early dinosaurs that take advantage of open terrain. The appearance of these animals corresponds with the tectonic changes that reshape the environment. Each new basin and volcanic plateau provides ecological opportunities that accelerate evolution. On land, forests of conifers and cycads spread along fault-bounded valleys where groundwater seeps collect. In the oceans, the gradual renewal of circulation supports thriving marine faunas, including the first ichthyosaurs and plesiosaurs, marine reptiles that herald a new era of dominance in the seas. The return of tectonic motion affects the planet's climate in other ways. As the continents shift and mountain chains rise or erode, atmospheric circulation adjusts. The once monolithic pattern of planetary monsoon weakens, replaced by regional systems of trade winds and storm tracks. Deserts contract in some areas while expanding in others. These climatic variations, though modest compared to the extremes of the previous ages, shape the evolution of both flora and fauna. Seasonal rainfall supports the spread of vegetation into former deserts, stabilizing soils and enhancing the drawdown of carbon dioxide through photosynthesis and weathering. Slowly, the Earth enters a new equilibrium warmer than the modern world, but stable enough to sustain complex life for tens of millions of years. The interior of Pangea, once defined by rigidity, now trembles with subtle motion. Earthquakes mark the boundaries of rifting zones, and volcanic activity paints dark scars across the landscape. Yet these disruptions do not herald disaster but transformation. The energy released by the planet's mantle continues to recycle its crust, closing one chapter and opening another. The supercontinent, having witnessed Earth's greatest dying and the long rebirth that followed, begins to divide under the same forces that first created it. In time, the fractures will widen into oceans, the deserts will become coastlines, and the cycle of assembly and dispersal will proceed anew. The final act of Pangea's story begins quietly, not with violence, but with the slow insistence of motion. Beneath the supercontinent, the same convection currents that once brought the continents together now begin to pull them apart. The forces of expansion that have long gathered in the deep mantle find paths upward through zones of weakness created by earlier rifting. Crust stretches, thins and sags along lines that will become the outlines of new oceans. At the surface, valleys deepen and widen, filling with sediment and water. Basaltic lava seeps through fissures, cooling into black rock that marks the earliest boundaries of what will one day be separate continents. These are the first fractures of Pangea, narrow shifting scars that extend from one margin of the world to the other. The great land mass, once stable and whole, begins to divide into the continents that will later drift to their modern positions. The earliest and most significant of these fractures develops along the region that will become the central Atlantic Ocean. As the crust stretches under the combined stress of mantle uplift and horizontal extension, faults form parallel to one another, creating a system of grabens and ridges. In these depressions, rivers and lakes gather, depositing red sand and clay that will harden into the characteristic Triassic and Jurassic formations of eastern North America, northwestern Africa, and western Europe. Volcanic eruptions accompany this stretching, their basalt flows spreading across the rift valleys in sheets that extend for hundreds of kilometers. Each eruption adds new layers of rock filling lowlands and shaping the architecture of future continental margins. The gases released into the air, mostly carbon dioxide and water vapor, alter climate again, but this time the change is moderate. The planet remains warm, but the extreme heat and instability of the Permian are gone. Farther east, the Tethys Sea expands as the continents that form modern Asia, Africa and Europe shift and rotate. Subduction zones along its margins consume older crust, while new oceanic basins open to the west. The complex geometry of these movements twists the edges of the supercontinent, producing mountain ranges and island arcs that mark the transition from the old world to the new. In what will become Antarctica and Australia, the crust also begins to separate, though more slowly. These southern rifts remain shallow and filled with sediment for millions of years before deepening into true ocean basins. The disassembly of Pangea is not a single event, but a drawn-out process that continues well into the Jurassic, each pulse of extension mirrored by the birth of new oceanic crust. The landscape of this world reflects the dynamism of transition. In the rift valleys, freshwater lakes and temperate seas alternate with periods of dryness, forming variegated layers of shale limestone and evaporite. These basins teem with life adapted to instability. Early dinosaurs, amphibians, and crocodile-like reptiles move along the shorelines, leaving trackways in the mud that will harden into fossils. Insects hover over pools rich with algae, and plants reclaim the disturbed soil as soon as volcanic ash settles into fertile ground. The ecosystems that emerge in this time are resilient, shaped by constant change rather than stability. Evolution accelerates as species adapt to shifting habitats, producing the diversity that will define the Jurassic Age. As the supercontinent fragments, the global climate becomes more varied. The immense continental interior that once produced such extreme temperatures no longer exists. Instead, multiple smaller landmasses surrounded by oceans experience more moderate conditions. Moisture circulates more evenly, and regional climates differentiate into tropical, temperate, and polar zones. Rainfall increases along the new coastlines, feeding rivers that carry sediments into the forming ocean basins. Vegetation expands in both density and diversity, covering hillsides with forests of conifers, ginkgos, and cycads. These plants in turn support a growing variety of herbivorous reptiles and early mammals. The Earth that emerges from Pangea's breakup is a greener, wetter, and more dynamic planet than the one that preceded it. The ocean chemistry adjusts in tandem. As new seafloor forms along spreading ridges, hydrothermal vents inject minerals into the water, enriching it with iron, sulfur, and other elements. The circulation of ocean currents intensifies, distributing oxygen throughout the depths and preventing the stagnation that had once suffocated the seas. Marine life responds swiftly. Ammonites diversify, corals reappear in shallow tropical waters, and new groups of marine reptiles fill the open seas. The Tethys, now broad and deep, becomes a center of biodiversity, connecting tropical and temperate ecosystems across vast distances. The ocean that once carried the marks of death transforms into an engine of renewal. On land, tectonic activity reshapes geography at every scale. Mountain chains rise where subduction compresses the crust, creating new highlands that influence rainfall and river systems. Volcanic arcs form islands that migrate slowly across the seas, serving as stepping stones for plant and animal dispersal. The Earth's surface becomes a mosaic of moving plates, each carrying life along shifting trajectories. Fossil records from this time show clear evidence of biogeographic separation. Species that once ranged across Pangea begin to diverge as oceans widen between them. This isolation becomes one of the engines of evolution, driving the radiation of distinct faunas and floras on every emerging continent. The mantle beneath the planet continues its steady turnover, recycling old crust into the deep interior, while creating new seafloor at spreading centers. The heat that once accumulated under Pangea dissipates more efficiently through these fresh pathways, stabilizing the planet's internal energy balance. Earth settles into a mode of slower, more distributed tectonic activity. Yet even this calm is relative. Earthquakes and volcanic eruptions remain constant reminders that the planet's crust is a transient skin over a restless core. The supercontinent's cycle assembly stability and breakup has reached its final stage, but the process itself will repeat many times in the ages to come. The breakup of Pangea also redefines the planet's atmospheric circulation. The newly opened oceans act as vast heat reservoirs, moderating temperature differences between poles and equator. Winds become more regional, forming the modern pattern of trade winds and westerlies. The large-scale monsoon that once governed the entire hemisphere weakens, replaced by smaller systems tied to specific basins. These changes influence rainfall distribution, bringing regular wet seasons to some regions, while leaving others in persistent dryness. The climate's newfound variety fosters ecological complexity, allowing diverse habitats to coexist across the globe. In the geological record, the first fractures of Pangea are preserved as sequences of basalt, sandstone, and evaporite that appear on every continent. They form a global fingerprint of separation linking distant regions through shared origin. The red beds of the Newark Basin in North America, the Karoo Basins of southern Africa, and the rift deposits of Western Europe all tell the same story of a supercontinent pulled apart by the slow persistence of internal energy. Above these strata Jurassic rocks document the flourishing of life in the New World. Dense forests, dynamic river systems and seas, alive with ammonites and marine reptiles. The transformation from unity to fragmentation marks not an end but a renewal, a shift from the stillness of a single landmass to the rhythm of a planet in motion. As the fractures widen into true oceans, the memory of Pangea fades into the structure of the continents themselves. Mountain ranges rift valleys, and oceanic ridges preserve the lines of its assembly and its disassembly, written into the Earth's crust like the closing pages of a long book. The planet has returned to motion, the continents drifting across the mantle, as they will continue to do for all the ages that follow. Pangea's time has passed, but the lessons of its creation, its dominance, and its fragmentation remain embedded in every grain of sand, every layer of rock, and every fossil that bears witness to the power of a world that was once one.